So these are second order circuits, and they have a resistor, an inductor, and a capacitor. And the reason they're called second order is if you set up an equation to solve for them, you end up with a second order differential equation. And if you get the circuit in a certain form, so if you can reduce it easily enough to where you have it all in series, so you have a series RLC, or in parallel, where your three elements are in parallel, then you can come up with a differential equation that's, I'll show you that in a second, that you can use to solve for that circuit. And the solution that you get it shows you what the current or voltage is at any time t, and there's three possibilities for the solution. And this is going to be the case anytime you have a differential equation that has a solution that has an oscillatory response, so oscillates, because what can happen is that the inductor charges while the capacitor discharges, and then vice versa. And so the current can be going one way and then it can be going the other way. Now, a critically damped circuit reaches its response in the quickest time and the smoothest time. And so this critically damped curve right here in the middle, the blue one, is showing that's critically damped, and that corresponds to having a couple parameters in a certain way. And then if you have underdamped, the top graph is showing charging, and the bottom graph is showing discharging. If you have something that's underdamped, then you're going to see where you have that oscillatory response where it goes above the final response, and then below, and then above, and then below, and then it oscillates like that. It doesn't reach, well, it might reach the final value first, but it doesn't stay there because it keeps going. And that's underdamped. And then overdamped, if you look at the top graph, you can see the green curve, it's not approaching as fast, and the same thing on the bottom curve. So you can tell if you have overdamped, underdamped, or critically damped by looking at your values of R, L, and C. So you look at R, L, and C, and you compute alpha, and alpha is called the damping coefficient, and it's R over 2L. And you also compute what's called the resonant frequency, omega naught, and the one that I have there, I just have the one for series. The one for parallel is 1 over 2 RC. So you compute alpha and you compute omega naught, and you compare alpha to omega naught. Alpha is the damping coefficient, and if alpha is bigger than omega naught, then you're damping too much, that's overdamped. If they're equal, it's critically damped, and if alpha is less than omega naught, then it's underdamped. So those are the things we're going to be looking at. And then if you can draw your circuit so that it looks like something that's just in series or just in parallel, so we have a series circuit or a parallel circuit, then these differential equations, these would be the differential equations that you would come up with if you did KCL or KVL. And so the first column here shows the differential equation, and then the second, well, if you simplify it by making something equal A, something equal B, something equal C, then you just get a simple second order differential equation like you see in this third column here. And once you get that, you can have a solution. So that's what this chart is for, is to save you the time. So you're learning how to solve differential equations in your differential equation class. You're going to use that Laplace transform method later on to solve more difficult circuits. But for these simpler circuits, you can say, well, it's just a simple second order differential equation, and these are the solutions. And so if you can get it in that form, and you just identify a few key values, then you have the solution, and you don't have to actually solve the differential equation because it's solved for you. So that is the introduction. Any questions? Okay.